In this video, we're going to take a look at substitution versus elimination reactions and what kind of factors are important when deciding whether a reaction will proceed by substituting the leaving group or the elimination of the leaving group and an atom on the adjacent carbon. Those factors include the location of the leaving group, whether it's on a primary, secondary, or tertiary carbon, how you classify the type of nucleophile. Is it neutral? Is it an acid? Is it a weak base? Is it a strong base? Is it very bulky and sterically hindered? And then also what kind of solvent is present. So first I want to just compare what substitution versus elimination is, and I'm going to use 1-bromopentane as the example for this. So in a nucleophilic reaction, you have to have some group that is on your organic substance that can leave and be replaced or just leave with the electrons. And so bromine, and I'm circling the electrons also, is the leaving group. It is on a primary carbon, and bromine is a good leaving group. So if you have a nucleophile that comes in and goes after the carbon with its electrons so that it wants to form a bond with that carbon, then bromine will leave and you'll have a bromide, and you will have your original carbon chain, but you'll have that nucleophile on the end. Everything else will still be present. This is the substitution reaction. A nucleophile has substituted for bromine, which is the leaving group. In an elimination reaction, elimination reactions actually eliminate your leaving group, but it also eliminates a hydrogen on the adjacent carbon. Not the same carbon, but the adjacent carbon. So in an elimination reaction, you end up making a double bond, or you end up making a pi bond. If you do this twice, then you get a triple bond. And so this is still the leaving group, and the leaving group will leave with its electrons. You still would have a nucleophile, but if the nucleophile couldn't get to this carbon, it would go after a hydrogen on the neighboring carbon. And so if our nucleophile came in and couldn't get to this carbon, an alternative would be for it to try to bond to a neighboring hydrogen. Well, the hydrogen, whenever a hydrogen leaves, it does not leave with its electrons, it leaves the electrons behind. And so this pair of electrons would go into a bond between this carbon and the one that has the leaving group, and that leaving group would leave with its electrons. And so you will end up, everything is the same, except the leaving group is gone, and this pair of electrons between carbons 1 and 2, there is now a double bond. This hydrogen is gone, and this bromine is gone, and so the end carbon still has 2 hydrogens. The second carbon has 1 hydrogen, and then the rest of the carbons still have all their hydrogens. Elimination, you make an alkene. Substitution, you just replace directly the leaving group with whatever the nucleophile is. But with elimination, the final product doesn't have the nucleophile or the bromine on it. And so up here you have the bromide ion present in solution. Here you have the bromide ion present. And you have the nucleophile, but it's bonded to the hydrogen. So whatever the nucleophile is, if it's likely to take on a hydrogen and become more stable, then it's a possibility that it would take a hydrogen off and become a product that has that hydrogen from an elimination. So we're going to compare two examples. I'm going to start with the 1-bromo-pentane, same example as we had. So the three things that are important: the location of the leaving group. This is on a primary carbon. In most circumstances, when the leaving group is on a primary carbon, it undergoes a substitution reaction. And so here we have our leaving group, and I'm going to circle the electrons with it because the leaving group leaves the electrons. And if we have a nucleophile, and so I'm going to choose the ion of ethanol. So ethanol that has had its hydrogen removed. And so this is a nucleophile. It's better because it's negative. Lone pair. This lone pair is going to try to bond to that hydrogen, and it's able to get to the hydrogen because it's a primary carbon, so there's less things in the way. When this goes in bonds, the bromine leaves with its electrons, and you end up on the end here. I'm going to draw the carbon chain first. So the original carbon chain, which is 5 carbons, all the hydrogens are still here. The end carbon still has 2 hydrogens, and it doesn't matter how you draw them because it's not, it doesn't have any kind of stereochemistry that would make it be R or S. And so this end carbon now, the bromine is gone and it's bonded to an oxygen. So you draw a bond to an oxygen, and then the oxygen is also bonded to a CH3. So whatever the nucleophile is, if it bonds to it, all of the nucleophile is still present, just one of the pairs of electrons is there. And then the bromide is now not bonded to anything. Now this could go back and forth because all these reactions can be equilibrium, but this is not a good leaving group, and so it's less likely to go back and turn back into this reactant. So this is a substitution, and it is an SN2. The reason that this reaction occurs is because you have a really good, strong nucleophile, and it bonds to that primary carbon, and it forces the bromine to leave. If you have the same reactant, but your base is a little bit different, and so if instead of having this nucleophile, we have this nucleophile, It's still an alcohol that has lost its hydrogen, so it's a negative ion. But instead of the alcohol being bonded or the oxygen being bonded to one carbon, that one carbon is a tertiary butyl group. And so the one carbon is bonded to three other carbons. And so this nucleophile, the portion that will go after something, it has attached to it a carbon that is tertiary. And so this is called a bulky, strong base. And when this happens, this particular base right here, when this happens, this oxygen that has all these carbons attached to it, it's going to have a hard time getting access to this carbon because this carbon is tetrahedral and it's next to another tetrahedral and there's a lot of atoms in the way. And so it cannot get to this carbon very easily. So instead, it'll go after the hydrogen on an adjacent carbon. So not the hydrogen for the carbon where your bromine is. So this is still primary. It'll go after the adjacent carbon's hydrogen. And so this will cause an elimination reaction. And so this bond between the carbon and hydrogen breaks, and this hydrogen is going to bond to this oxygen to form an alcohol, tertiary butanol. This pair of electrons will then go and form a bond between the first and second carbon and force the leaving group to leave with its electrons. So we end up with that product. We end up with this product here. So we have 5 carbons. All the ones that are not part of the carbon 1 and 2 situation, they stay the same. So CH3, CH2, and CH2. Now I'm going to circle what goes away so we can keep track. 1H on carbon number 2 goes away, and the bond, the pair of electrons is now going to be used for a bond between carbons 1 and 2. This carbon number 2 still has 1 hydrogen, and carbon number 1 still has 2 hydrogens. This is an elimination reaction. And the reason it occurs is because we had what's called a bulky strong base. Anytime you have this base, it will cause an elimination reaction. And the type of elimination reaction is an E2, where the 2, just like SN2, the 2 means that the nucleophile and the organic reactant are both reacting in the same step of the mechanism to produce the product, E2. It's a second order reaction. So we're going to compare that with bromine that is on the second carbon. And so this is secondary. So your leaving group is on a secondary carbon, which has different properties. And the reason, again, why, is because in order for a substitution reaction to occur, the nucleophile has to find a way to get to the carbon. And it's very difficult to get to this carbon. And so I have got a resource here, and this is available on Moodle. And so this is a flow chart, and it allows us to kind of figure out specific situations that can get kind of complicated. So our first reaction was primary alkyl halide. And is it benzylic or allylic? And ours was a no. Ours is just a primary alkyl halide, so no. Is the nucleophile a hindered strong base, like tertiary butoxide? Yes, ours was for that last reaction. So it was an E2 reaction, which creates an alkene. our first reaction, no, it was not a hindered strong base, so it was a substitution reaction. If it's a secondary alkyl halide like ours, is the nucleophile an anion? And so it's going to depend on whether we have a yes or a no. And so we are going to look at an example when we would have a substitution, and we're going to look at an example where we have elimination. Okay, so I'm going to react this with the same methoxide that we reacted our 1-bromopentane with. And so this is a strong base. If you have an alcohol and you remove the hydrogen and it becomes an anion, it is a strong base. It's actually stronger than hydroxide. So it is a strong base. So the product, it will depend on whether this oxygen is more likely to attack a neighboring atom's hydrogen, or can it get to the carbon? And in this case, it is going to be more difficult to get to the carbon because it's not a carbon on the end. This has 2 other carbons that have hydrogens, so they're all tetrahedral. And so it's going to be more difficult, and since this is so strong, something being strong means it's more reactive. And so this chemical here, this oxygen, we got 2 adjacent hydrogens over here, 2 carbons. We're going to show it going after one of the interior carbon's hydrogen, not the one at the end. Okay, so this is going to end up being an elimination reaction. So in an elimination reaction, you go to the adjacent carbon, and in this case, you're going to go to a carbon that's on the interior that has less hydrogens, and you're going to remove the hydrogen. When the hydrogen is removed in an elimination reaction, those electrons go between the adjacent carbon and the carbon that has the leaving group. So here's my leaving group. It's going to leave. So this is the hydrogen that is going to get removed right there. And so we are going to end up with these first 2 carbons being the same. So it's going to be CH3, CH2. And then this is the carbon that lost a hydrogen. And so that's going to have 1 hydrogen still. And instead of having a single bond between this and carbon number 2, it's going to have a double bond. Carbon number 2 will have lost the bromine, but it still has a hydrogen. And so it will have a hydrogen. And then there'll still be a CH3. So if we take a look at our little flow chart, we have a secondary alkyl halide. Yes. Is the nucleophile an anion? Yes, it is. Is the nucleophile a strong base like sodium OR? Now the OR means the R group is just some kind of carbon. So it just means an alcohol that has lost a hydrogen. So this is an anion. All these are anions. Yes, it was. So we just showed an E2 reaction. E2, you get an alkene, and the alkene forms between the carbon that has the leaving group and an adjacent carbon that has lost a hydrogen. So this was an E2. Okay. So what if we didn't use the oxide version? What if we just used methanol? So this still has the hydrogen. And so this is not real reactive, so it's not going to react quickly. And so in this situation here, this has hydrogen bonding. And because there's hydrogen bonding, and this is a very good leaving group, when you put the alcohol and you mix it with the 2-bromopentane, some of this leaving group will start to leave. And so it's secondary, it will leave, and you will make the cation carbon number 2 is now a cation. It still has hydrogen and it's still bonded to the CH3 on the end. This is occurring in equilibrium. It goes back and forth, and that bromide is over here. So in this solution, once this starts happening, once you add the alcohol, then the bromine will start to leave, but the bromide and the alcohol are both present. If the bromide goes back onto the molecule, you get the original. That's the equilibrium part. But if the alcohol, which also is, this is partially negative, if a pair of electrons on the alcohol, that's what makes it a nucleophile, it's going to be attracted to this positive, and it's going to be very attracted because that's positive and this is partially negative. If one of these pairs of electrons goes in bonds, then we will get this product. Okay. This hydrogen is still attached to the oxygen up here. It's positive. This here does not go after a neighboring hydrogen because it's only partially negative, not a full negative charge. And so it's going to be more attracted to this positive. This hydrogen here is not partially positive, so it's not going to be real attracted to that hydrogen. It's most likely to bond to here. So you end up with this nucleophile being substituted where the bromine had been. And since it occurs in 2 different steps, first the bromine leaves, then the nucleophile starts to attach, then it is an SN1 reaction. The rate determining step is this reaction here. So if we go back to our little flow chart, is it secondary? Yes. Is the nucleophile an anion? No, it was not. It was neutral. Is the substrate an alcohol? No, substrate would be the alkyl halide, not the nucleophile. No, then it is SN1, which is what we just did. So this is one example of a way that you can make a decision is with the flow chart. There's also a table that is available, and in the table it has what the structure of your alkyl halide is, the reactivity of the nucleophile, the concentration, the solvent, and the how it affects the stereochemistry for each of them. And then down here, it's just do you choose substitution versus elimination, and it's just solely based on is it a methyl primary, secondary, or tertiary. So either one of these are good places to go. It just depends on your method of thinking. There's also a summary of how do you look at the nucleophile. Are they a base? Is it strong or weak? And so this breaks down whether they are a strong nucleophile and strong base. So nucleophile dash base. And so the first word is it a strong nucleophile? That's strong nucleophile, strong base. This is weak nucleophile, strong base, strong nucleophile, weak base, and weak nucleophile, weak base. So the reason there's 2 words is because the first word is what kind of nucleophile is it. The second word is what kind of base. And it is the classification of these that determines whether it's going to be SN1, SN2, and also E1, E2, or substitution and elimination. And so this document, there's really good a good summary. And so if it is a weak nucleophile, strong base, oftentimes these, meaning why it's a weak nucleophile, that means it's not good at actually bonding to your organic substance. It's better at just being a base, and bases still hydrogens. So these two things are really good at taking hydrogens away. So use these resources to complete some of the practice problems that are listed.